Okay, is the following long statement going to be true? And I'm not really going to say the statement out loud because it's very long and there's a lot of brackets, so you're going to have to really observe. I'm not going to say it out loud when I'm writing the proof either. I'm just going to write it. So how can we tell if this is true or not? Well, let's write out some diagrams, right? We're dealing with 3 sets, so we need to have 3 sets. So the first thing you should think of probably is going to be the case where all 3 sets share something in common, and let's label them. That'll be our A, our B, and our C, okay? And then on the right-hand side, we're going to want to draw the same thing to represent the right-hand side of the equation, okay? Next, what do we want to do? Well, let's try and shade in the area the left-hand side is going to be interested in. So the left-hand side is going to be interested in A union B, which is going to be, of course, this entirety of A and the entirety of B shaded in. However, we don't want for this shaded area to have any part in C, which means any part of this shaded area that's in C, we don't want, which means we want to erase the parts of it that are in the set C. So we can erase this section, and this last section over here. So we're going to be looking for this type of shaded area on the right-hand side. Well, let's see. Okay, what is the shaded area of A minus C? Well, the shaded area of A minus C is going to be A, all of the set A, minus the parts that are also in C, which means we're going to be interested in this part over here without shading in these two, because these two are going to be in C, and we don't want A to have any parts in C, so we only shade in the parts that are not in C, okay? Then we want to take B minus C. Well, B minus C is going to be the same as A. It's going to be all of the set A without any of the area that's in C. So we're going to want to shade all of B that's also not in C, which is going to include not shading in these 2 areas. Okay. Now we take these 2 shaded areas and we just want to take the union of them. So we want to keep both of them, right? And look at the shape. Well, it looks like, yeah, this is going to be true. The shaded areas and sections are going to be the same on both sides. Let's just try, for the sake of argument, a few more examples to really be sure that this is going to be equivalent. Okay, so let's have a look at these 2 examples. In both of these examples, 2 of the 3 sets share something in common, and 1 of them doesn't share anything with either of the other 2. In this case, we have A and B share something, and in this case, we have A and C share something. So let's have a look at the case where A and B share something. Well, A union B is simply going to be all of A, which is going to be something like this, shaded in with all of B, right? So there we go, okay? Then all of A and all of B minus C, we don't want to include in the shaded area any part that shares anything with C. And none of this shaded part shares anything with C since C is distinct, so we just keep this as it is. So that's going to be the shape we're going to look for on the right-hand side. So are we going to find that here? Well, let's have a look. So A minus C is going to be all of A without us shading in any part that's in C. Well, none of A is in C, so we can just shade all of A. Similarly, we want B minus C. B minus C is everything in B, but it's also not in C. So we want to shade all of B, but not shade the parts that are going to be in C. But none of B is in C, so we just shade all of B. And the union just means we want to take both of these shaded areas. So here we have both of the shaded areas, and what do we find? Well, yeah, the left-hand side is in fact equal to the right-hand side. Well, what if we change it? What if we make C one of the sets that shares something with the other 2 sets? Well, let's have a look then. If we have A share something with C and then B be distinct, what are we going to find on the left-hand side? Well, A union B is going to be all of B shaded with all of A. And then we're going to want to remove any part of these shaded areas that overlap with C. Well, the only parts that overlap with C is going to be this part here where A overlaps with C. So we're going to want to erase that. So there we go. This is the shaded area. This is the shaded shape we're going to look for on the right-hand side. Are we going to find that? Well, let's see. A minus C is going to be all of A that's not in C. So that's going to be an area that looks like this. Right? We're not shading in this middle part because this middle part is going to be in C, and we don't want anything to be in C. And similarly, we want B, but not in C. So we want to shade all of B that's not in C, which is just going to be all of B, since no part of B is going to share anything with C. And we want the union, so we care about both of these shaded areas. Well, what do we find? We find it's going to be the same on the left and the right-hand side. So this is really enforcing this statement is probably going to be true. Let's just try one last example. So there's a lot of different combinations of set diagrams you can draw with 3 sets, but I'm just going to do these 5 because these 5 should cover most cases. So the last case we're going to look at is, what if none of the sets share anything in common with each other? Is the left-hand side going to be the same as the right-hand side? Well, what are we going to find? A union B is going to be all of A, and all of B shaded in. We're going to want to look at all of those. And then A union B minus C means we want to take this shaded pattern and take away or erase any part that overlaps with C. Well, none of it overlaps with C, so we just leave it as it is. All right, now let's see if we find the same thing on the right-hand side. Well, A minus C is going to be all of A that's not in C, which is just going to be all of A since none of A is in C. And similarly, B minus C is going to be all of B without us shading in any part of B that's in C or overlaps with C. And no part of B overlaps with C, so we just shade all of B. And then the union of these 2 sections is going to be us caring about both sections, so we don't need to erase anything. So it does look like the left-hand side is equal to the right-hand side. So I think it's pretty safe to assume the statement is true, so let's go ahead and prove it. All right, so before we prove this, we have to recognize this is an equivalence statement, which means we need to show everything on the left-hand side is going to be on the right-hand side, and everything on the right-hand side is going to be in the left-hand side. Or mathematically, it means this side, this set, has to be a subset of this set, and this set has to be a subset of that set. Or, in mathematical words, it means the following. So it means the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. We're going to be showing both of these are true in our proof, and then in our proof we can say that when this is true and that's true, that means our equivalence is true. So let's do that. So to start off with, this is going to be a for all proof because we're looking at any sets A, B, and C, right? We're not putting any restrictions on what A, B, and C can be. That's why I did so many examples, because they could have any relation to each other. They could be anything, right? So let's go ahead and say that because it's a for all proof, we start with let. We say let A, B, and C be sets. Fantastic. And now we can get into our first case, which is going to be to prove that the left-hand side is a subset of the right-hand side. Okay, so to prove our first case, we're going to want to show that any elements in the left-hand side, A union B all minus C, is going to be also in the set A minus C union B minus C, which means that if we create some element X, it means we have to show that any element X in this set will also be an element of this set. Fantastic. Okay, so how are we going to do this? Well, let's break apart what it means for X to be an element of this set. It means that X must be an element of A or X must be an element of B, but in both cases, X cannot be an element of C. Fantastic. Okay, or actually, more explicitly, I keep forgetting to do this. It's more so as saying X is an element of A union B, and X is not an element of C, and then we can break apart what it means for X to be an element of A union B. This means X is an element of A, or X is an element of B. Fantastic. So what can we do? Well, we need to get from here somehow to our goal. So we need to somehow get A minus C, and we have to get it so X is going to be an element of B minus C. Okay. Well, we know that if X is an element of A, and X is not an element of C, then X is obviously going to be an element of A minus C, which puts X to be an element of our goal set. And similarly, if X is an element of B, then X is going to be an element of B, but not an element of C, since in both cases it's not going to be an element of C, which puts it also as an element of our goal set. Fantastic. So we've sketched out our proof. Now let's go ahead and put this into words. So we start off by saying, well, let's take our representative element, X, and suppose it, right? We say, suppose there exists some element X in A union B, all in a bracket, minus C. Fantastic. Then, as we did here, we want to break apart what it means for X to be an element of this set. We say then X is an element of A union B, and X is not an element of C. Fantastic. Okay. We can say that, we'll say full stop, and we can say since X is an element of A union B, then X is an element of A, or X is an element of B. Fantastic. if x is an element of A, then x is still not an element of C, so x is an element of A minus C. Fantastic. And we can say, yeah, I'll put a full stop there. Thus, x is an element of A union, not A union C, A minus C, all in a bracket, union with B minus C, right? Since x is an element of this part, doesn't matter what you union that part with, x is part of this, so it's part of this set. Fantastic. Now we want to do the same thing where if x were in B. So we say, if x is in B, then x is still not an element of C, so x is going to be an element of B minus C. Thus, x is going to be an element of A minus C union with B minus C. Fantastic. And now that we've shown x as an element of our goal set in both cases, we can say, therefore, since x is an element of A minus C union with B minus C in both cases, then we can now conclude that this is going to be true. A union B, all in a bracket, minus C is a subset of A minus C union with B minus C. So there we go. We've proven that the first case is going to be true. Now let's go ahead and try and prove the second case. Okay, so in our second case, similar to how we did it in our first case, we want to show that any element, like y, a representative element that will represent any element in this set, if we can show that y can also be an element of our goal set, then since y is an element of both and y represents all the elements or any elements in our first set, then that makes the first set a subset of our goal set. So how are we going to do this? Well, similarly, what does it mean for y to be an element of this set? Well, it means that y is an element of A minus C, or y is an element of B minus C, which gives us more cases. It gives us our ifs, right? Which means we have to break this apart. Well, if y is an element of A minus C, then y is going to be an element of A, and y is not going to be an element of C. Fantastic. And then if y is an element of B minus C, then we know y is an element of B, and y is not going to be an element of C. Okay. Now let's focus on the left-hand side. Well, if y is an element of A and not an element of C, because y is an element of A, then y is an element of A union B, and since y is not an element of C, then we can conclude this. Similarly here, since y is an element of B, then we know y is going to be an element of A union B, and since y is still not an element of C, we can conclude back to our goal set. Okay, so we've sketched out our proof. Now let's put this into words. We'll start by supposing our representative element, y. We say, suppose y is going to be an element of A minus C unioned with B minus C. Fantastic. Now, as we did here, we want to break apart what that means. So we know that then y is an element of A minus C, or y is an element of B minus C. Fantastic. So now we have two cases we need to look at. We need to look at the case where y is in here, and look at the case when y is in here. So we say, if y is an element of A minus C, then y is going to be an element of A, and y is not going to be an element of C. And, yeah, I'll keep writing on the right-hand side. Since y is an element of A, then y is an element of A union B, comma, making y an element of A union B minus C. Fantastic, okay? Similarly, now we do our second case, if y is an element of B minus C, it's basically going to be verbatim with what we did with A. So we say, then y is an element of B and not an element of C. And since y is an element of B, then y is going to be an element of A union B, making y an element of A union B minus C. And since in both cases we can conclude, or actually I'll keep writing here, since in both cases y is an element of A union B minus C, then, comma, we can conclude what we were trying to prove. A minus C, close bracket, union B minus C, close bracket, is a subset of A union B minus C. Okay, there we go. We've proven both of our cases to be true, so all that's left is to write our conclusion, which is basically going to say that since this is true and that is true, that makes this true. So we just say that. So we can conclude that since first case is true and the second case is true, then of course our original statement is going to be true. So here we go. This is our final proof.